Yesterday we looked at what a radian measure of an angle was. So we looked at if you had a circle and it has a specific radius, say in this case that this is maybe 3 centimeters as a radius, that the arc length, if I let this arc length be 3 centimeters long, so I measure out and have this arc length be the same measure as the radius, that we find out that that would be 1 radian for the angle measure. So yesterday we talked about that the arc length divided by the radius will help us calculate what the angle is measured as in terms of a radian measure. Well, today what we're going to look at is if, on the other hand, we have a arc length, we have a specific angle, and we want to calculate what the arc length is if we know what the angle is. So kind of moving backwards. Yesterday we talked about if you have a specific arc length and a radius, what will be the angle measure. Now we're going to work backwards. And if we think about, if I gave you a circle like so, and it has a radius of r, and I want to determine how long this arc is, but this time I tell you what the angle measure is, we're just doing basically the inverse operation of what we had done previously. So if I have a circle, say that is given a radius of, let's say this time 4 centimeters, and let's say I tell you that I have an angle here that is equivalent to 3 pi over 4 radians, and that's the angle measure, I can now ask you, how long is that arc? So in our case, if we think about just figuring it out, we know what the arc length is if we travel all the way around the circle. All the way around the circle, this circle would have an arc length of its circumference, which is 2 pi times the radius. So that would be the arc length if I went all the way around the circle. Now we're not all the way around the circle. We're only 3 pi over 4 radians around the circle. But we know that all the way around the circle would be 2 pi radians. So we're a fraction of the way around the circle. So if I take the circumference and I multiply the circumference by the fraction of the angle that I have as part of this circular sector, I know that I have 3 pi over 4 out of 2 pi is how far I've traveled around my circular sector. All the way around, if I went 2 pi radians would be the circumference of 2 pi times 4 centimeters, but I've only traveled 3 pi over 4 radians through my circle. So this fraction is the portion of the circle over which I have my intercepted arc being calculated. So here's a figuring out version of doing a calculation based on some, I don't want to say common sense, but doing a calculation based on what we previously understood as for using our circumference and multiplying it by the part that we have. So we can see that if we simplified this, the 2 pi's would cancel out, and we end up having 3 pi over 4 times 4 centimeters. And when we do this calculation, we'd find out that that actual length of that arc would end up being the product of these two, which would end up being 3 pi in centimeters. Now, curiously, if I look at this, this ended up being the angle, and this was the radius. And you might question and think, so the arc length, S, that I got looks like it ends up being the angle in radians times the radius of the circle. And you think, well, maybe that just worked that time, that one particular time. And it ends up, let's look up here at the worked out version I have on the sheet. If you have a generalization, if I have a circular sector being struck by this angle, and I know that this angle measure is in terms of radians this time, so theta is in terms of radians, and I want to calculate what this arc length is for this particular circle that has a radius of r, here's a generalization of what I did in my earlier calculation. I know that the circumference of the circle is 2 pi r, and I know I have a fraction of it. I had theta, in our case in my example, I used 3 pi over 4 out of 2 pi, but in general, if this angle is any measure in terms of a radian, not a degree, theta out of 2 pi would tell you the fraction of the circumference that you're going to have. And look what happens when we do a little simplification on this. The 2 pi's will reduce down, and in effect, you will always have the arc length equal to the angle that you had from your intercepted arc of your central angle, measured in radians, times your radius. Now this is a very helpful formula. Typically it's given as S equals r theta. It's also true that S equals theta times r. But memorizing formulas, again, can sometimes be cumbersome if you have a lot of things to keep straight. You should always remember that the circumference of a circle is 2 pi r, and if I multiply the circumference of the circle by the fraction of the circle that I have, which would be, in this case, the angle in radians divided by 2 pi, which is all the way around the circle, I can always come up with that formula. Now, what do you do if your angle is in degrees? Well, let's just look at another little example. So if I have an angle, a circle, and I want to know how long an arc is, and let's say I just have a little, say this is a 25-degree angle, and let's say that this has a radius here of 3 inches. And if I wanted to determine how long this arc is, well, I know what it is to go all the way around my circle. It's 2 pi times the radius. And I know I don't have the entire arc of going all the way around, or the whole circumference. I only have a little fraction of it. Doing something similar to what I did up above, I only have 25 degrees of the circle out of an entire 360 degrees. So that's the fraction of the circle I have now if I'm dealing with a radian measure. So I have the circumference times the fraction of the circle that I have in terms of degrees, as opposed to up here I did the fraction of the circle I had in terms of a radian measure. But same idea, circumference times what fraction of the circle do you have. I generalized that here in this little formula. Okay, so you can see that the calculation is basically the same. It's just a matter of what your angle is given and what you'll be using as the fractional denominator portion of your formula. This one does simplify down nicely. I suppose you could end up doing a little bit of simplification here too and take the 2 and divide it into the 360, but I think it's more valuable to remember arc length can always be calculated by taking the circumference times the fraction of the circle you have. Now, we can generalize that as well when we're dealing with area, and we'll do that in a minute. I have 2 examples here that show, once with degrees, once with radians, of how to find the perimeter of a specific, in this case, pizza situation. You can see I drew a picture. I have a pizza that has a 14-inch diameter, so a radius of 7 inches, and I wanted to find what would be the perimeter. So I'd have this edge, the 7-inch edge, another 7-inch edge, and I basically have an arc that I have to calculate. The circumference of the circle, all the way around, all the crust, would be 2 pi times the radius, or I could have done pi times diameter here, would have been fine as well, times the fraction of the circle I have, which means I have a sixth of the circle. So I can determine my perimeter. Now, had my discussion been in terms of a radian measure, a pi over 4 radian slice, same basic idea. I drew my picture. I have 7 inches, 7 inches, and then I have the arc length that I need to calculate to determine the perimeter of that piece. And I could circumference times the fraction that you have, pi over 4 radians out of 2 pi. Now, these 2 pi's will cancel out, and it will simplify to this calculation, which in effect, arc length, if I know my angle in radians, is going to be r times theta. Now, if we're going to calculate the area of a pi sector, we'd want to use exactly the same type of proportional reasoning. We know how to find the area of a circle. Area of a circle is pi r squared. And if you want to have a fraction of that area, I can likewise do the same type of computation. Area is pi r squared. That's if I have the entire circle. However, if my angle is in terms of a radian, I only have a portion of that circle, then I need to multiply it by the fraction of the circle I have, and that would be in theta out of 2 pi being all the way around. So that would give me the fraction of the area that I would have. Likewise, same thing takes place if my angle was given to me in terms of degrees. I know how to find the area of a circle, and I figure out what fraction of the area I have. This formula is quite typically simplified down. You need not memorize this other simplified version, but the pi's would cancel, and this is commonly written down as 1/2 r squared theta. I happen to know the formula. I don't recommend that you memorize this formula. I recommend that you remember the idea of taking area times the fraction of the angle of the proportion of the circle you have, whether it be in radians or whether it be in degrees, and I think that's an easier format to use. And so now the section questions will, with these ideas, will allow you to be successful with those.